now we move on to the next session for the invited talks. And in this session, we are very fortunate to have Professor Abhinav Gupta. Abhinav is an associate professor at the Robotics Institute at CMU and also a research manager at Facebook AI Research. Abhinav is renowned for his research on self-supervised learning systems for a variety of computer vision, robotic manipulation, and visual navigation problems. His works have won Best Paper awards in top robotics and computer vision conferences and received media coverage, including BBC, Wall Street Journal, and Wired, and so on. I've been deeply inspired by his pioneering works on scaling up robot learning in the real-world environment, and I'm very excited about what Abhinav is going to share with us today. So that, Abhinav, please take it away.
Thank you. Can you hear me?
Yep, it looks great.
Okay. And you can see the slides as well, right?
Yep, everything looks very clear.
Okay, thank you. So thanks for the invitation. Today I'm going to be talking about something really different and I'm super excited about, but this is the first time I'm presenting it. So the slides are in a very rough shape, but hopefully you can, by my excitement, you can see how critical this one is. All right, so I guess all of us know the story of this past 5 years. We have made significant advances in RL, robotics, starting from AlphaGo to all these Atari games, navigation, and even robotics, right? We are seeing robot manipulate, like grasp objects, manipulate, and even like this really good example from OpenAI, which basically they are trying to manipulate the Rubik cube using the shadow hand, which was first done in simulation and then transferred to the real world. So for this talk, I mean, initially I'm going to focus on the navigation part for the time being. And so let's focus on navigation itself. So in the navigation domain, there are two main problems that are looked at, especially from the learning perspective. So the first problem is the image goal navigation. So let's say you are in a new scene that you have never seen before. You're dropped anywhere in the scene, and now you're given an image as a goal, and you have to reach that goal location. And so the thing that defines your goal is the image itself. And so you have to go navigate, avoid all the obstacles and reach to that goal. Another one, which is similar, is the object goal navigation. And so in this case, I'm going to say something like find a toilet, and now toilet seat. And now you have to go and navigate and reach that toilet seat and so on. The reason I'm calling this as semantic navigation is because to solve this task, humans would use lots of semantic priors, right? I mean, so if I tell you go to a toilet seat and you're in a living room, you would assume that there must be some kind of a powder room nearby. And if you cannot find any powder room nearby, you will try to go to one of the bedrooms with which one of the toilets might be connected and so on. So over the years, we have basically built idea of how do homes look like. And from there, we have basically built idea of how do you solve these problems if I'm in an unseen environment and so on. And so this is kind of what I'm saying here, that we need to learn semantic priors of the world. And so to solve the toilet seat problem, I need to say, okay, toilet seats are found in bathrooms. Bathrooms are attached to bedrooms. And so let me go and find a bedroom. And so if you're in a hallway and it's a 2-floor duplex apartment, you would say, oh, let me go to the second floor because generally bedrooms are in the second floor and so on. And I would say we have made a lot of progress in this area of navigation. And so this is one of the examples I'm showing. This is not the semantic navigation. This is a point goal navigation. And so like Habitat, which is one of the simulators where they showed that with 2 billion frames, that you can get 90% performance on point goal navigation. Point goal navigation does not use a semantic, but I'm just trying to show that we have done a lot of progress in this last 3 years, even in the tasks like navigation and so on. And so I have been thinking, why have we had this progress, right? I mean, what is the reason behind this progress? And so I went ahead and asked a lot of people, and I can go ahead and ask a lot of people even in this room and say, okay, why do you think you're making so much fast progress in robotics and RL and all this stuff, especially from the perspective of robotics? And people tell me that, oh, the first reason is, of course, we have these now new scalable RL, not new, but I mean, these scalable RL approaches, we have basically made infrastructure around the RL, which is going to make it much, much simpler for us to scale up. And the second reason, which a lot of people tell me, is simulators. Right now we have these nice simulators like Habitat, Thor, and many more. I mean, I'm just picking up random, any two, which are mostly used for navigation purposes. And so the simulators have made it really possible. For example, like Habitat, like the navigation, the point goal navigation task that I showed, they show that with 2 billion frames, you can solve point goal navigation to 90% accuracy or whatever. And that is only possible with simulators and so on. And so if you kind of poll the people, that would be the top 2 reasons why we are making this progress. I mean, even for OpenAI Rubik Cubes, simulator was a big thing. Like they could train for 13,000 years on a simulator and so on. But I would say whatever has made it work has now become the biggest bottleneck in my mind, at least. And so if you think of scalability, RL is not sample efficient. 2 billion frames of simple task as point goal navigation, then think how many frames you would need for much more complicated tasks like opening with screwdriver and so on. And similarly, on the simulator side, with simulators are very expensive to build. And we have just made first dents into the navigation-based simulators. Think about all the contact physics and tactile things, and you have to put so many other to make the data rich in a simulator. You'll have to do so much effort. So what has worked for us with these RL and simulator, the 2 things that are primarily accounted for, I think now they're becoming bottlenecks, definitely on the scalability side. And similarly, on the diversity side, simulators will have much less diversity, because for every environment that you have to add, you have to do a lot of engineering. You have to define where the collision surfaces are. You have to do the full 3D mapping and so on and so forth. And so I have been wondering, I mean, like when what works for you becomes the biggest bottleneck, you remove them essentially, right? That's what we did in self-supervised learning. We have been doing as well. Like supervision was what made deep network work. We cut down the supervision because supervision was now becoming bottleneck. We were not able to label more images anymore. Similarly, for me, RL and simulators are now becoming a bottleneck. So let's just cut down RL and simulator completely from the picture, and maybe then we can scale up. And so I have been asking this question, do we actually even need RL and simulators for navigation? And I'm going to start with navigation, because that's the, like you start with the simplest task and then you go towards harder and harder tasks essentially. Because if I can train a navigation policy without any RL and without any interactive data, because simulators provide you interactive data, like you can try, collide, and then restart and collide and keep doing this. So if I can cut RL and interactive data from my pipeline, then the sample efficiency goes away. And I can basically simply train my policy from these passive data of videos of people roaming around. And that is much more easy to scale, because there are already millions of videos of people roaming around in houses for tours, real estate tours, and other reasons as well. And so in this talk, I'm going to try to move away from RL and simulators for navigation, semantic navigation, and we are going to try to do self-supervised learning from passive data, and more specifically from videos of people roaming around in houses. We will try to learn a really good navigation policy, image navigation policy. And so what I'm going to show is how you can basically build up this self-supervised approach to learn policies from passive data. And most importantly, I think this is the most exciting part. We are not only going to show that you can do something like achieve some good results here, but in fact, you can beat all the baselines as well, in fact. So, and that kind of tells you that we need to be really vigilant about the claims that we'll make with RL and simulators and so on, because in a lot of cases, you might be able to beat them out without actually using either simulator or RL and so on. So we are going to show these state-of-the-art results in with a very, very simple approach. And I think that kind of highlights the excitement for me and really. So before I go into the detail of the approach, let me try to understand. Let us take a step back and understand, why do we need RL and simulation? Why are we even on this path of using RL and simulation for navigation? So the reason people use RL is, the first reason is that you might have a goal defined, right? I mean, and so RL is going to be used for credit assignment, right? If I have 2 or 3 possible paths, I need to know that this path is much better for me, because I'd get much better reward by going these trajectories and so on. So RL, the first reason why people use RL is you can get full credit on the goal, but you also need to give credit to the intermediate states. And that's why you need RL to basically figure out which intermediate state is useful for me and which intermediate states are not useful for me and so on. So that's the first reason why people would RL. And the other reason why people need use policies is because you might want to take this path on the left, but it's going to lead to a dead end. And so you need to plan, like your policies are kind of incorporating into this like longer term reasoning, essentially in RL. And so that's the reason why anyone would say we need to use RL for navigation itself. Now, what I'm going to argue here, that at least for the sake of navigation, we just don't need any credit assignment. The task is so structured that our problem is to go to the goal. And geodesic distance, like the distance, like number of steps needed to take the goal, the distance itself tells you how to do credit assignment by itself. Whatever reduces your distance most is the best state that you should be using, like how you should be giving the most credit to that state essentially. So because navigation is such a structured problem, we really do not need to do any credit assignment is my first claim. And the second claim, in fact, I'll go even a step further and I'll say that we actually don't need any policy. We are just going to have states. We are going to predict the distance of the states from the goal and then just use the greedy. We are going to say, oh, out of these 10 states, this seems to be reducing the most distance. I'm going to take it. I don't care about what's happened in the future. Let's be greedy, essentially. And what we are going to show is that these simple tasks like predict distance, use greedy is just going to help you solve the task much more efficiently and much more in a much more better manner, essentially. Now, let's understand why people use simulators, because that's the second thing you want to cut, right? And so simulators are used for first using the ground truth, right? I mean, you need to give rewards to your policy. So simulators are basically, with simulators, you're able to create random goal locations and you're basically able to assign like reward shaping, and you can do all that stuff with that thing. And the second reason I think, which a lot of people would argue simulators are still critical for, is this whole idea of negative data for obstacle avoidance. So the idea is that you can try to implement your policy. If you go and collide, you say, oh, this is a bad policy. So all this negative data that you will gather by collision. So if you're looking at just passive videos of humans roaming around in the scene, then from there, you will not get any collision data. And if you do not have any negative data, can you learn a meaningful policy is a question that we are. And so simulator provides us this opportunity to learn what is good and what is like obstacles and what is good and what is bad, the negative data in that area. And so again, what I'm going to argue is that what we are going to do is we are going to, with regards to ground truth, we do not care about exact ground truths or anything like that. We are just going to learn an approximate distance estimator from passive data. From videos, passive videos, you can use something like SLAM, which might not work on perfectly, but it will basically give you some rough idea of poses. And from there, you can basically just learn approximate distances. Okay, this is 5 meters away probably from your goal image and something like that, essentially. Because anyhow, we are using semantic priors, and semantic priors are very weak. So we really don't need a perfect distance function estimator. All we need to say is out of these three options, which is the best option for me? And an approximate distance estimator is probably good enough here. The second thing, what I'm going to also argue is that this whole idea of needing the negative data or collisions to actually learn a meaningful policy is not really required, because what we are going to show is that just locally, you just try to avoid obstacles, which you can do by using depth image or predicting local depth. And so you can basically take RGB and predict depth. And from there, you will know locally, if I move here, I'll collide. So the collision decisions have to be made very locally. You do not need to think farther ahead of, oh, if I continue on this path, I will basically go and collide 5 meters later or something like that. So just make good local decisions of collisions, and that is good enough. You don't need to plan further ahead in that area. So in summary, the idea what I'm going to do is going to be very simple. Let's say you are an agent. You have basically you're starting to go towards a goal, and you are currently at N3. Like you started at N1 state, then you move to N2 and N3. Now, as a next step, what you're going to do is you're going to predict out of 9 possibilities, which are the possibilities where you will not collide. And out of those 9 possibilities, you will also predict how far do you think, if I go to possibility 1, how far will be the goal from that location. If you go to possibility 2, how far will the goal from that location, and so on. So you just predict goal distances from each of the possible locations, unexplored locations. And then at that point of time, you just be greedy. You just decide, oh, this node seems to be telling me that I am the closest to the goal. So let me go here and try to reach the goal from that. And so this is going to be as simple as that, the basic core algorithm. Of course, this is the core, but there are some details here, which I need to sprinkle now. And so I'm going to basically spend the next 5 minutes. But the main idea, the basic idea is there. And so when I come to results, I can again, if you want to phase out, it's okay for the next 5 minutes. But so at the core of this NRNS algorithm is this topological map. So we are basically going to maintain a topological map. So the purple nodes are the nodes that you have already visited as an agent, and the blue nodes are the unexplored nodes. These are the nodes that you are going to try to say, okay, maybe I should go here, maybe I should go here, and so on. So our agent is going on a trajectory, on a path, and it keeps on creating these unexplored nodes as it is moving along. And we are going to try to predict distances of the goal from these unexplored nodes. And that's what we basically need to do. So we need to learn 4 functions to solve our problem. First is this global policy, which is the distance prediction. So we are basically going to, for all the unexplored nodes, the nodes that we have not visited yet, we are going to predict the distance, the geodesic distance to the goal from that node. Then we need to have a local policy. So this local policy basically says that if I have selected a node Ni as the one which has the lowest distance, how should I go from where I am currently to this next node? Like how should I locally maneuver so that I reach there? The third function is, once I reach to a new node, I need to add new unexplored nodes. How do I decide which new unexplored nodes to add to my graph? And the fourth one is, when I'm close enough to the goal, I will basically say, oh, I think I'm near the goal. Now I just need to keep moving towards the goal by predicting the point, converting into a point goal navigation task. Basically, we'll predict the theta and the distance again and again and basically move towards a target in that manner. So these are the 4 functions that we are going to use to solve this problem. The first function is this distance prediction. So again, this is the same setup. Like we will have the current image of the node, we'll have the goal image that we are trying to reach, and we want to predict all the unexplored nodes, what kind of distances will they have. And we will basically minimize, we'll take the node that will minimize the distance to the goal node essentially. And so what we do is we use a simple graph network. I'm not going to go into the detail of this architecture, but I mean, it's obvious that you take the node, convert it into some kind of graph. Then you have these graph attention layers, not graph function, graph attention layers. We basically have the adjacency node being represented by like these delta poses and so on. And then the goal image is represented as its own feature vector. And then you try to predict the distance of every node from your goal image essentially. And so this is like, this is one of the architecture we tried, which seems to work really good. I'm sure there are other architectures as well. And more things will come as people will do more research in this area. And so the final goal will be, of course, is what you are predicting the distance from the unexplored node, plus how far it will take you to go to an explored node. So we are adding the travel cost to go to an explored node as well. And so the final distance is basically how far your unexplored node is, plus what is the distance from the unexplored node itself. Now the local policy, we are going to use something very, very simple. We are not going to innovate here. Given the RGBD image, we basically can create local metric map, right? Because we can predict the depth maps to metric maps locally. And what our local policy gets as input is where you are currently, like what is the delta rho and delta phi that you want to go to as a next node. And so you are basically just going to make sure that you're avoiding all the local obstacles using the depth map and just keep try to reach your rho and phi. There might be errors here, but I think this seems to work reasonably good. This local policy, it seems to really, we are not doing any innovation here really at all. On the unexplored one, so this is one you have moved to a new node, like you are going to update your topological map with new unexplored nodes. So this one is actually very, very simple. Again, you are going to sample 9 directions from your node, like going right in front of you, 15 degree left, 15 degree right, and so on. So you sample 9 directions and then check if you see any collisions for the next 2 meters or 3 meters in that direction. If you are seeing collisions in that next 3 meter using the depth map, you say, oh, this must be a dead end later on or something like that. So you will not try to predict distance from there. You will just you will only predict distances for where you are seeing a lot of free space essentially. And so those will be the only unexplored nodes that you're going to add. This kind of avoids trying to predict distances for dead ends basically. And the last one is trying to predict when to stop kind of a scenario, because it is critical for navigation agents to know that they have reached the goal and when to stop. And so in this one, basically given the current node, you basically predict the goal, like given the goal image, you basically have a function that predicts whether the goal location is within the site of you, which that means it's locally within here. So if this is an example where you are seeing the goal image as being this office table and chair, it's in the view of the current image. So you say, okay, I have almost reached my goal. And so now I will just basically switch to my local policy, which is So now basically my policy will be like predict how far the goal is from me, and then try to move it there with local policy, and then keep doing it again and again. And so this is the final thing that looks like. So given a goal RGB image, you first predict you first predict the distances for unexplored nodes, choose the one with the lowest distance, then have your local policy go to that distance. When you move to the new node, you update your graph with the more unexplored nodes so that you have more places to go later on. And then finally, what you do is you keep at every time step after every move, you keep checking whether the target is within sight. If the target is within sight, you switch to this target policy, which is going to do. Okay, so this is how the simple algorithm looks like. So as you can see, what we are learning is this target distance prediction and the global distance prediction, and the function 2 and function 3 are kind of deterministic, so we do not need to do any learning there at all. And so the main thing that we need to learn is how do you predict distances basically. And so given, so what we are going to do is you're going to learn this distance function from the RGBD videos of indoor trajectories. And so these are the kind of like the data sets on which we'll basically show the results. And so what we need is like for training, what we need. So what we have is given a topological graph, we predict the distances of all the unexplored nodes. So all we need is this kind of training data really. So what we do is we basically take our RGBD video. We basically use SLAM if you're to basically predict some local rough poses of the video. From there, you basically get this stepwise trajectory. And from those stepwise trajectory, you do some kind of affinity clustering to make it behave like these higher level nodes. So this affinity clustering simulates that higher level nodes. Then you add some unexplorable nodes, so explorable nodes using the function, like from wherever paths that you traversed in the video, you add some other new unexplored nodes. And now for training your distance function, you sample some subset from the trajectory of the video. You say, I have traveled this subset. Now let me predict the distance function of all the remaining nodes, essentially. So you can basically subsample this is kind of similar to, yeah. I mean, so basically you're just subsampling different goals, and you're different graphs and training this with lots of subgraphs as well. So what, again, for experiments, you're going to compare it to imitation learning and reinforcement learning in a simulator. And so because imitation learning and reinforcement learning approaches are going to use simulator for training, they will be in distribution because we are going to end the day test in the simulator itself. So the first two experiments, we will also train on the simulator data, but videos only. So we will basically sample some videos in the simulator. We are not going to use the rest of the simulator or the active data from the simulator. We are just going to, so it's kind of like sample 10,000 videos from the simulator, and we are just going to use those 10,000 videos to learn our policy. On the other hand, imitation learning and reinforcement learning are actually going to use the simulator. Sorry, the reinforcement learning is actually going to use the simulator, and it's going to collide and do all that stuff that basically RL approaches do. So for apples to apples comparison, we are first going to train on videos of simulator. And then we are also going to show that you can actually take data from YouTube, VL Estate 10K, and the approach works really good as well. Okay, so to generate the videos from the simulator, we need to make sure that we are not using the shortest distance between the 2 points, essentially, right? Because someone can argue that if the human is doing the shortest distance path, then you are maybe just doing imitation learning, and that's it, and so on. So our videos are much larger, where you will have someone going to one point, then going to another point, so might make a U-turn. So the video is basically very large with U-turns and left and right turns and so on. So there is it's not just a video between two points and shortest distance. We sample 19,000 videos from Gibson, 43,000 videos from Matterport, and here are the results that we get. So we are trying it on 3 different settings. We are trying it on easy, medium, hard. So easy is when the goal is within 1.5 meter. The medium is when the goal is between 1.5 and 3 meter, and hard is when the goal is beyond 3 meters. And so basically so you have to make lots of decisions and so on. Another thing, so this is kind of standard. People do easy, medium, hard. But another thing that we did was we had space, straight, and curved. Because we are doing greedy policy, like we are making greedy decisions. Someone could argue that if your path is curved, if you are not following a straight path, then it is going to be a harder problem for greedy to work and so on. So we are showing that it's not the case. Like even on curved scenarios, greedy seems to be working really well. And so PPO is the reinforcement learning baseline. trained for 20 million frames. And even if you actually increase it further, there are papers which show that even if you go much higher frames, the performance does not go beyond the behavior cloning. The other baselines are behavior cloning with metric maps as memory or gated recurrent units as memory. And this NRNS is basically our algorithm. We tried to add a noise also, to the actuator noise, that if you are saying I moved 0.5 meter, maybe I moved 0.51 and so on. And even with that, the NRNS algorithm seems to be working really good. We also did some ablations to see out of these 4 functions, which functions are critical and which functions are not critical for us to learn, like how. And so it turns out that the distance prediction function is the most critical network function. So in this whole pipeline, which is kind of obvious, right? If you can predict distances, you have encoded almost all the semantic information that is needed to solve this task. And so that is kind of what I'm highlighting here, that distance prediction is the most critical part here. Just to show the full potential, we are also training it on YouTube real estate videos. So this is the real estate 10K data set. Here we are basically are again able to get significantly good performance on the Gibson. So we have Gibson. I'm explaining Gibson here, but Matterport is going to be in the paper as well. And again, what that thing to show is that you can train in simulator or you can train with YouTube videos. The performance is very, very close by. So it kind of tells you that it seems to be working, even though this video stuff is just using passive data, not using any simulation data. Since I'm running very much out of time, here are some of the examples to show. Sorry. On the top left is a start image. On the right is the goal image. And this is the kind of the path taken. And so you are seeing how the number of unexplored nodes keep on increasing as we are working. And you keep on making the selection using the greedy approach. Here is another example, which is a little longer path. And so in this case, you can see again, it takes a really good path. Okay, I did have another thing to talk about, but I think I'm really out of time. So just to end the talk here, I think while we've made this significant progress, I feel that the real challenge lies with learning a good representation. So here there was good representation for semantics, right? I mean, like the distance function encoded everything that you needed to include. And so you really do not need any RL or anything like that. So just good representation with greedy policy can go a long, long way. And so I'm not going to argue that you don't need RL, but at least it's a very, very strong baseline, which any RL-based approach or simulator-based approaches should be considering before actually making claims that you need any RL or simulator. And the best part which I like about this is our approach is going to be really scalable. Without RL and simulator, you can just use any data on the web. I mean, we did not go beyond certain limit, but we only stopped at the real estate 10K. But now the sky is the limit. Just find any videos and use those videos. You can really add diversity for the data. And efficiency, this one is very efficient to train. It's just self-supervised algorithm. There's no RL here as well. All right, with that, I think I'm going to stop since I'm really out of time. I can take a few questions if there are any.
Thank you so much, Abhinav, for the really inspiring talk. And for our audience, if you have any questions, please feel free to post it in the chat or directly use the raise hand function. So I have a question. So I think this, do you think this argument of like replacing RL and the simulation with passive data can be also applied to other robotics domains, such as grasping or multi-step like manipulation? And related to that, I guess when you use like passive data, you have to make some assumptions about your expert trajectories or expert policies, such as some of the things you have already mentioned in the talk. And do you think that could be, these requirements can also be met for, you know, for example, like robotic manipulation kind of tasks?
So I think there are two parts. I mean, first, I mean, we did not, if I'm not wrong, and I think on my co-author is there, I mean, we have no assumption on the, so these are not expert trajectories per se, because that's what I said, the trajectories could be U-turns, it could be anything. They're not expert. So if you're, what we are assuming is that approximately they will encode some good path, right? I mean, they might not be the best shortest path, but approximately human is not going to be, like if I sample 2 random points and I calculate the distance between them, it's not going to be really, really bad distance. Like we will avoid all the obstacles and so on and so forth. But so, I mean, that's why we made sure that we are not sampling shortest distances videos from the habitat and so on. And real estate 10K, actually, I don't know how trajectories are made. Maybe they are kind of experts. Maybe real estate tour people do make expert trajectories really. But that is just the data sample. Like some other data set we just used offline. We did not have any. So I would say there is not much assumptions there. The second question is, I think, really, really interesting question actually in my mind. Will this translate to manipulation and grasping? So I'm very hopeful, yes, and that's what our next project is really right now. We are basically trying to extend this to manipulation and grasping, and I think that would be the game changer, frankly. I mean, here I think I do agree that navigation is little easier, but I think we had to try on the easy setting first. So why is navigation easy? Because you can, by knowing that, like by doing this slam, you can know what exactly the human took the path. So you have a mapping from video actions to the robot actions, easy mapping really here. Whereas with manipulation, the easy mapping might not be there anymore, like between the robot action and between the video actions and the robot action. So that's what makes this a little easier. But I think this is a really good start in my mind because, but I have some ideas and I think my understanding is it should work. But of course, we also need to know how good the representation function we will end up learning. To me, at the end of the day, it's all about the representation function, the vision. So interestingly, I mean, I feel like vision is much more important than I initially thought in robotics. It's going to be like, if you have a really good vision function, probably RL is not needed.
Thank you. That makes a lot. Yeah, that makes a lot of sense. And so Yushan has another question.
Thanks, Abhinav. I think the argument of no RL, no simulation also applies to traditional navigation method, right? The SLAM-based method, they don't need RL, also no simulation. Right. I'm curious, what's the advantage of your method compared to traditional SLAM-based navigation?
I mean, you're right. I mean, so if you are looking at traditional methods for like point goal navigation and so on, they don't need, like, I mean, the planning-based approaches. So I mean, the way to look at it is, so traditional methods are either doing under the known maps. Here, this is completely unknown maps. So the core of our learning is, I mean, compared to traditional approach, the core of our learning is in this function which predicts the distance to the thing. Traditional methods will not be predicting that. I mean, so basically what we are saying is that if you can predict distances to the goal, if you can learn this function that given image 1 and image 2 can predict the distance between those two images, that's all you need is basically what we are claiming here. So I mean, you're right. I mean, I think in some sense, we are kind of building on traditional methods and saying, look, I mean, all this learning-based approaches, just use traditional methods, add this semantic prior on top of it and done. You are done. Basically, you don't need to worry about all this RL and all this nonsense that for billions of frames that you are doing. It just wastes time. And so I think in some sense, what we are saying is exactly that. Just use traditional methods, add your semantic priors that you can learn using self-supervised approaches nowadays very easily, and that's it. I mean, we are done kind of in some sense.
Thank you.
Got another question from the audience. So Tahir asked, thanks for the great interview. And in addition to this, my question, what's your opinion about offline RL for even more complex tasks?
Right. So I think that's a great question. I mean, my understanding of offline RL might be limited. So I'm going to take my understanding with a grain of salt. But in offline RL, you are assuming the rewards are still there, right? I mean, you have a table of observations, which is state, and then they're mapping rewards and so on. So I don't believe in rewards, frankly. I mean, anything that uses rewards is wrong, in my opinion, because the world has no rewards really. So we have to design our own rewards and so on. So with that opinion in mind, I mean, I'm not exactly sure from that perspective. For me, offline RL is just something on top of to make, like, you could not collect data in real RL settings. So let's do offline RL. I mean, it's in some sense the same, right? I mean, offline, online. I mean, so basically you're a little bit off policy in the offline RL versus in online RL. Maybe you're much more on policy because you're collecting the data as you're learning, updating your policy parameters and so on. So I think that's the difference. But overall, I mean, yeah, so this is very different from offline RL in that setting because there's no rewards really we are saving from the simulator. So offline RL is still using simulator. Offline RL is still creating all the data set and it's saving the rewards. So it does still need the ground truth map and so on. I would say, in fact, our previous paper on this series, so this is not something that we reached in one, like we have been doing it, worked slowly and slowly. Previous paper was kind of saving the ground truth maps and so on. So So that would be more close to offline RL, but this one is kind of just getting rid of any RL-ish, any rewards in RL and other things. Yeah, just saying, just simple distance function. And I think, I mean, for me, I mean, going back to the manipulation question, which is, I think, in my mind, the biggest question for me right now is, I actually feel again with manipulation, it's the same thing. I mean, right? I mean, you are basically want to open this, let's say, cup. You have the goal state. Now you have this initial state. You just keep on doing your distance mapping from that goal state, and you should be able to solve this. So all we need is a good vision module which understands what is closer to the goal state, what is farther to the goal states, and that's it.
Yeah, thank you. Let's thank Abhinav again for the great talk and the answers. And yeah, if you have more questions, feel free to just send to us. And Abhinav won't be able to join us again in the panel discussion, but if there are any specific question, we can forward it to Abhinav.
Yeah, also feel free to email me. So this paper is going to be on archive very soon. It's not yet there, but I did not want to wait for not talking about it. So in the next 1 week, we'll be uploading the paper. So, but in the meantime, if you still feel interested in asking a question, feel free to email me as well.
Yeah, thank you.
Thank you.